Hello, in this lesson, I would like to talk about the properties of a continuous function or continuous functions. Let's recall the definition of a function that is continuous at a point A, which is the limit of the function as x approaches A is the same as the value of the function at point A. So we know that this involves three elements, right? We have that discussion earlier in those other videos before this one. But we also have some nice properties about continuous function. Okay, so this section, we're going to talk about the properties of continuous functions. In other words, adding, subtracting, multiplying, dividing, multiplying by constant, even composition. So we're going to address that issue on composition as in a little bit. Okay, so F composite, that's also going to be addressed. Now, if we know two functions are continuous, right? Obviously, you can see if we get a continuous function to find limit is this direct substitution. So direct substitution is very good to use once we know we can do that, right? So this theorem says if f and g are continuous and at A, and c is a constant, then all of these are going to be continuous, provided denominators is not zero. Okay, I'm gonna remove this one first because the setting for composition is slightly different. So when we are there, we're going to talk about it. And what is more, we have other properties too. Any polynomial is continuous everywhere. We know polynomial is defined everywhere, right? So to find the limit of a continuous function of a polynomial, it's just direct substitution. And we've done that many times over. Any rational function is continuous wherever it is defined. In other words, it is continuous in its domain. And root function is continuous in its domain, direct substitution. Trig functions are continuous in their domain, right? So trig functions, we're talking about sine, cosine, tangent, cotangent, secant, cosecant. We know their domain. And arc sine, arc cosine, so inverse trig functions are continuous in their domain. Exponential functions are continuous in their domain, and logarithmic functions are continuous in their domains. So all of these are very nice properties. So all we have to do is that we know the domain of all of these functions when we are looking for its limit, it's just a direct substitution. Nice to know. So let's look at this example. So let's call it example number 1, okay? Just for this particular lesson. So we'll kind of remember it. We're interested in this rational function's limit when x approaches -2. And then according to that rational function is continuous everywhere in its domain, then the question is -2 in the domain, right? So what is the domain? Right? What is the domain of this function? Which is x squared minus 2x minus 2. Well, as long as the denominator is not 0, so we know how to find this domain. So 3 minus 2x should not be 0. And as a result, x cannot be 3/2. And obviously, -2 is in the domain. And therefore, to find, right, to find the limit is just a simple direct substitution. We just directly substitute. And we can drop the limit sign, replace x by -2, replace x by -2 everywhere where x showed up, right? Replace x by -2. So we found the limit already, right? The rest is just a calculation, just a calculation. So -2 is, that's a 4, and that makes another 4. So the total of these is 8. 8 minus 1 is a 7. Denominator is 3 minus 2 times -2. That's going to be a 7. And equals to 1. Done. Finished. Okay, it's a direct substitution. So we use the theorem to find the limit of the function. And the next question asks, where is this function continuous? Where is this function continuous? To answer this question, we need to know the domains of all these functions involved. The denominator, right, cannot be 0. That's one requirement we must satisfy. And secondly, for ln x, x must be greater than 0. That's the domain for ln x. And thirdly, for arctangent x is defined everywhere. So this x can be any real number, right? So that's not going to be any restrictions. We must satisfy these two conditions, and that will be the domain. And ln x is continuous in its domain. Arctangent is continuous in its domain. And x squared minus 1 in the denominator, as long as this is satisfied. So we're basically applying these properties, subtracting, dividing. All we have to do is guarantee the denominator is not going to be 0. So our ultimate domain will be determined. Okay, so let's solve this inequality. The first one, we will get x squared not equals to 1. Okay, and we take square root on both sides. That should not equal to square root of 1. Square root of 1 is 1. And the absolute square root of x squared is absolute value of x. So that should not be 1. In the end, x cannot be positive 1. It cannot be negative 1 either. All right. And the next part, the domain for ln x, which is x greater than 0, if we combine these, right? If we combine these, and we found that, well, x cannot be negative 1 will be guaranteed if we apply this. So the domain would be, okay, x is larger than 0. And x cannot be positive 1. X cannot be positive 1. All the other numbers, it is continuous. So this will lead us to the following intervals. One interval would be 0 to 1, and the other interval would be 1 to positive infinity. Okay, so that's where this function is going to be continuous. So we can say this function is continuous or in, okay, when we have an open interval like this, in this interval, in these two intervals. All right, so that's example number 2. Let's look at example number 3. We evaluate this limit. Sine function is continuous everywhere, cosine function is continuous everywhere. We're looking for this limit. Is this function continuous? Yes, this function is a continuous function divided by the sum of 2 other continuous functions. And this entire function is continuous everywhere because the domain, okay, so if you notice the domain is all real numbers. Why? Why domain is all real numbers? Because cosine x is between -1 to +1, right? For any real number. For any real number x. Okay? So 2 plus cosine x for sure is always going to be 2 plus cosine x is for sure it's going to be always greater than 0, right? If it's greater than 0, then it's not 0. So this function is continuous everywhere. So this function as a whole is continuous on the entire domain, in this entire domain. And pi is just one of the numbers. To find this limit is just a simple substitution. Okay, so we drop the limit sign and replace x by pi. Replace x by pi. Okay, and what does that equal to? The top sine pi is 1. Sine pi over 2 is 1. The bottom is 2 plus cosine pi is -1. So the whole thing is equals to, the limit is going to be equals to 1. That's all. Okay. Now the next one, we're going to look at this very interesting property that involves composition. Okay, because here we actually see the composition, right? What about the continuity of functions that are in composition? So here we go. Okay, so we understand how this works, right? We understand how this works. So f of g of x. So first of all, f is continuous at b. And what is b? B is the limit of the function g as x approaches a. So in this case, okay, it basically says if x approaches a and f is continuous, and is g continuous required? No, g continuous is not required. It only asks g is to be having a limit when x approaches a. You can see in this theorem, it did not require g to be continuous. It only requires g has a limit when x approaches a. That needs to be taken paying attention to. So if we can do that, we can take the limit across the continuous function f. Okay, take it inside. Take it inside. Okay, so no. Okay, f is continuous. Continuous at b. Okay, that's the first condition. Second condition, basically, it did not require g is continuous at a, actually, as a matter of fact. So this, in other words, it just have a limit. So having a limit is a weaker condition than continuous at a. Okay, so this condition is good enough. It did not require it is continuous at a. if these two conditions is satisfied, we can take the limit across the continuous function, go inside. So that what the theorem says. See how we apply this theorem. Okay, how we apply this theorem. This should be example number 4. Okay. All right, we have this theorem available to us. Okay. Now, we know arcsine function is a continuous function in its domain. Okay, arcsine function is continuous in its domain. Okay, and x approaches 1. Okay, x approaches 1. The question is, right, if this is the f, this is the f, right? And the g is the function inside. Does this function has a limit? Does this function has a limit? So in order to do that, we can assume g of x, if you like. You don't have to introduce g if you don't want to. But assuming this is a g, and we want to see if g has a limit. If g has a limit, right? So we want to see if g has a limit as x approaching 1. We want to observe this limit. Basically, we're checking this condition. We're checking this condition. So g, there's x approaching 1. This function inside the parentheses is g here. To simplify, obviously we cannot do direct substitution here. Why? Because that's going to cause the denominator equals to 0. Okay, but what we can do is that we can do a simplifying. We can do a rationalization. Okay, so I'm going to do 1 plus root x divided by 1 plus root x. Okay, we multiply by 1. Anything times 1 stay the same. And then we get to the next step. We get to the next step. On the top, right, the bottom, we have x minus 1 minus x. And this is 1 plus root x, right? So this is 1. So these two multiply, that's a squared minus b squared. So it's going to be 1 squared minus root x squared. So this part is gone. Okay. And next, this piece is going to be x, and that's just going to be 1. X approaches 1, but x is not 1. In fact, x cannot be equal to 1 domain-wise. So these two can be reduced. These two can be reduced. Okay. Let me write one more step though. 1 minus x. Let me write one more step. Okay, so you can see. One more step. This time I'm going to reduce it. Okay, reduced. Now we can do direct substitution. We can do direct substitution. Direct substitution, we're going to replace x by 1. So this is going to be replaced by 1. So that limit is 1/2. Okay, so we refer to the limit that b is 1/2. Now the question is arcsine continuous at half, right? Is arcsine continuous at 1/2? Because this says f is continuous at half, at b is half, right? The answer is yes, because arcsine is continuous. is continuous in its domain. Okay, and what's the domain for arc sine? The domain for arc sine is from -1 to +1, and 1/2 is in it, right? So i.e. arc sine is continuous at 1/2. And see, to apply the theorem, we have verified these two conditions. F is continuous at the limit of g when x approaches a. That's what we have demonstrated. So next, we can apply the conclusion of this theorem. Okay, so I'm going to bring this conclusion right here at the bottom so you can see the comparison. Okay, so in our case, and obviously x approaches 1, and what we have is this piece. Okay, so this is what we have. So the arc sine, so it's arc sine, right? Limit of g, x approaches 1, and that g is over here. Right there. We have demonstrated the limit at x approaching 1 of g that equals the whole of it is equals to 1/2. So this limit is going to be replaced by its limit 1/2. And arc sine 1/2 equals to pi/6. Okay, so this is how the theorem is applied. And then you say, well, what if g is continuous at a? Yes, if g is continuous at a, then this conclusion will also be true. Okay, if g is continuous at a, and this will also be true. So that answers the question for composition. Okay, so that is basically the next theorem. Okay, that's basically the next theorem. Okay, so I like to show you that. If g is continuous at a, f is continuous at g of a, then the composition function f composite g given by this is continuous at a. So that's this theorem basically is the direct conclusion of that theorem. Okay, so if both functions is continuous, in other words, right? If both functions is continuous and that their composition is continuous. Okay. Let's see, this should be example number 5. Okay, this should be example number 5, not 9. Okay, we'll just redo the numbering. Number 5, where are the following function continuous? Okay, so let's look at A, x squared. So we see this function g of x. Okay, so let's do it one by one. So this function, g is viewed as the composition of sine function composite with x squared. Okay, so this is the composition of sine and x squared. Okay, so this function, well, x squared is continuous everywhere, and sine is continuous everywhere, right? Therefore, g of x, so you can see g of x is continuous everywhere in real number, negative infinity to positive infinity. And for f of x, right, for b, over here, it can be viewed as a composition, right? It's a composition. It's a composition of two functions. Composition of ln x, and 1 plus cosine x, 1 plus cosine x, right? 1 is continuous, cosine x is continuous everywhere. So 1 plus cosine x is continuous everywhere in real number. ln x, however, is continuous for x must be positive, right? So we need to figure out the domain for this function. Let's see, what is the domain of this function? So to determine the domain, we need to ensure 1 plus cosine x must be larger than 0. And this implies, okay, cosine x has to be what? Okay, subtract 1 on both sides. Cosine x has to be larger than -1. We understand, okay, cosine x is always between -1 to +1. So how do we combine these two conditions, right? Cosine x cannot be equal to -1, in other words, right? Anything larger than -1 is okay. Cosine x is always greater than or equal to -1. So we just eliminate, right? We just have to eliminate. So let me put this one over here. Let me put it here. Okay. So the number need to be excluded is exclude. Okay, exclude x such that cosine x equals to -1. What are those numbers? Those numbers that will cause issues of continuity. Okay, so what are the values will cause cosine x equals to -1, right? And so those values are going to be what? X equals to, well, cosine is an even function. Okay, so plus minus pi, right? What else? Plus minus 3 pi, plus minus 5 pi, right? All number multiples of pi are the numbers that it cannot be, right? So 2k plus 1. X. We need to exclude these x's. What does that mean? Right? So we're asking the function is continuous. We have to exclude these numbers. Okay, so let's look at a number line. Oops. Let's make it darker. Okay. So we look at these numbers. Right? So it cannot be pi, right? It cannot be 3 pi. It cannot be 5 pi. and everywhere in between, okay, so there will be negative pi, negative 3 pi, right? So on these intervals, f of x is continuous. It's continuous. All right. So how do we describe this? We can list these intervals, right? So these intervals will be the difference between these intervals will be let me write it as the intervals. We can describe these intervals, okay? The intervals, so these intervals are going to be like 2k plus 1 pi, 2k plus 1 pi, and this quantity plus, okay, because the difference between pi and 3 pi is 2 pi. 3 pi to 5 pi, that difference is 2 pi. And negative pi to pi, that's 2 pi. Negative 3 pi to negative pi, that's 2 pi. So all we have to do is just plus another 2 pi. Plus another 2 pi. Okay, so these intervals, okay, f of x is continuous. Is continuous for any k, for any integer k. Any integer k. That's it. Okay, you can see it combines with knowledge on logarithm function and the trig function. Okay, logarithm function and trig functions. All right. Yeah, you can simplify this. I hear you. Okay, so if you combine these two, it's going to be plus 2. This is going to be plus 3 pi, really. Okay, if you're going to simplify that, right, it will turn into, well, because this is 2k pi, and factored out the pi, so plus the 2, so this is going to be 3. There. So that's what the interval looks like. So you have many small intervals. All right, I think that's the end of this lesson, I believe. Thank you for watching.